so-called mixing via shearing method, which is a geometric approach and has the advantage first to give you some quantitative estimates as well, and it's generalizable to many other situations, in particular to time changes, which is the focus of the second part of the mini course. In the fourth lecture, we will define what time changes are and look at some basic properties, and we will also prove ergodicity and mixing. And then in the fifth lecture, we will try to address the question, when is a time change isomorphic to the unperturbed flow? And we will look at some rigidity results in this direction, and I will state Ratner's rigidity theorem and try to give some ideas behind the proof. And then in the final lecture, if we have time, and it will depend on how the rest of the course go, we will try to go beyond SL2R and try to look at time changes and other types of perturbations in different groups. So, okay, for today, we will focus on background materials. So in the first part, we will introduce the group SL2R, which is the main protagonist of this course, and its Lie algebra. I will tell you what homogeneous flows are, and in particular what the Horocycle flow is. And we will also introduce the Haar measure, which is the invariant measure with respect to which we want to study the ergodic properties. And then in the second part, we will also introduce some more objects that we will need later. So we will introduce the adjoint action and the Lie brackets and try to look at their dynamical interpretation. We will introduce the killing form, which we will need to see why and how G, the group G, acts in the hyperbolic plane. And finally, we will introduce the Casimir operator, which will play an important role in the next lectures. Okay, and please feel free to interrupt me at any point if you have questions or if I'm going too fast or too slow. Okay, so let me start by introducing what homogeneous flows are. So we will focus on the group SL2R that I will call G, and this is the group of 2x2 matrices with real entries and determinant 1. So elements of G, I will always denote them with a boldface letter. And these are matrices A, B, C, D, where A, B, C, D are real numbers, and the determinant is 1. So AD minus BC is equal to 1. Another group that will play a role later is the group PSL2R. That is the quotient of SL2R by its center, consists just of plus or minus the identity. E will denote the identity matrix. And PSL2R, you can think of it as elements of PSL2R, you can think of them as 2x2 matrices where the entries are up to a plus or minus sign. Okay, so we want to start by looking at this group, and we can think of it as a submanifold of R4, right? So we have four real entries, they satisfy some conditions, so we think of it as a submanifold of R4. So as a very schematic picture, maybe you can think of SL2R as some curved object inside R4. And so the first thing that we want to do when we have such a thing is try to linearize it. So we want to look at tangent spaces. And we have for example, we can try to understand what the tangent space at the identity is. Because it's a linear space, so it's easier to understand. So let us look at the tangent space at the identity. I will call it G, little g, with this Gothic font. And I think of them as the geometric tangent vectors. So what are they? I look at all possible smooth curves, gamma, defined on some open interval containing 0 with values in G, and such that gamma of 0 is equal to the identity. I look at all curves of this type, and I then take the derivative as 0. And this will be a 2x2 matrix with real entries. And I want to look at what this collection of matrices are. So for example, if you take as a curve gamma 1 of t being 1, t, 0, 1, okay, so this is a curve of elements in SL2R, so these matrices have determinant 1. It's smooth because the entries are smooth functions in t, and at 0 is the identity. So if I take the derivative of this curve at 0, I get by definition an element of my tangent space at the identity. So if I differentiate this with respect to t, I get the matrix 0, 1, 0, 0. And I will call this element U. Okay, I can take another curve, for example, this diagonal matrix, where on the entries you have, on the diagonal you have e to the t over 2, 0, 0, e to the minus t over 2. Again, for any t, these matrices are in SL2R, the determinant is 1. The entries are smooth function in t, so this is a smooth curve. S0 is the identity, so again, if I take the derivative, I get this matrix, 1/2, 0, 0, minus 1/2. And this, by definition, is another element of my tangent space. And I will call this guy X. And as a third example, you can do the same with the matrix 1, the curve of matrices 1, 0, T1. And again, if I take the derivative as 0, I get 0, 0, 1, 0. And this is a third element in my tangent space of the identity, and I call it boldface B. Okay, so these are three elements in little g, and if you look at them long enough, you notice that all these three matrices, they have in common the fact that their trace is 0. And indeed, this is not a coincidence, and we can actually prove that the tangent space of the identity, this collection G, consists precisely of those 2 by 2 matrices whose trace is 0. Okay, so let me sketch the proof of this lemma. So first we can prove that this G is a vector space. So how do we do this? Okay, let's take two elements, gamma prime of 0 and eta prime of 0 in G. So these are two geometric tangent vectors that correspond to two smooth curves, gamma and eta. So I need to prove that their sum is again an element of G. How do I do that? I define a new curve that I call gamma times eta. So gamma times eta at t is equal to, by definition, of gamma t times eta of t. This again is a smooth curve that at 0 is the identity, it takes value in G. So if I take the derivative of this curve at 0, by definition, I get an element of my tangent space at the identity. And the derivative of this at 0 by the product rule is the derivative of the first, gamma prime of 0, times eta of 0, which is the identity, plus the first at 0, which is the identity, times eta prime of 0. So I get precisely the sum of gamma prime plus eta prime at 0. So I prove that the sum of two elements in little g is again an element in little g. And I can prove also that if I multiply an element in little g by a scalar, I still find an element of little g. How do I do this? Well, I define a new curve, gamma sub a, defined by gamma sub a of t equal gamma of a times t. This is another smooth curve with with value in SL2R, that 0 is the identity. So if I take the derivative, I get an element of G, and the derivative at 0 is by the chain rule a times gamma prime of 0. So this proves that little g is a vector space. So in the previous slide, we found three elements that belong to G. So since we just proved that G is a vector space, the linear span is included in little g. And if you think 1 second, you realize that the linear span of these three guys consists precisely of the space of 2 by 2 matrices with 0 trace. So we have already one inclusion, that this linear space is contained in G. So now we have to prove the other inclusion. So assume that now you have a curve, a smooth curve, with the property that the at 0 is the identity. So its derivative at 0 is an element of G, and now we want to prove that this is a 2 by 2 matrix with 0 trace. So since gamma of t is an element of SL2R, its determinant is equal to 1 for all t. So if I differentiate this equation at 0, I get, on the left-hand side, I get 0, and on the right-hand side, I get the derivative of the determinant. And if you just write it out, so if you imagine that gamma t as entry AT, BT, C of t, and D of t, and you differentiate with respect to t at t equal to 0, and you remember that gamma of 0 is the identity, you get precisely the trace of the derivative at 0. So if gamma of t is a curve in G, then the trace of the derivative at 0 is equal to 0. And this proves that G is included in this linear space. So this proves the equality of this. Other questions? Okay. So more in general, you can look at the tangent space as some other element of G, and you can see that actually the tangent space at some other matrix of your group, it consists precisely of the product of one matrix W that was in the tangent space at the identity times G itself. And you can see this, for example, by noticing that any curve that goes through G is in one-to-one correspondence with the curve that goes through the identity multiplied on the left by G. So the tangent space at little g is in one-to-one correspondence with the tangent space at the identity. And the one-to-one correspondence is take an element in here, multiply by G, and you get an element in this tangent space, and vice versa. If you multiply by G minus 1, you end up with an element in the tangent space at the identity. So all the tangent space are basically the same as the tangent space at the identity. So this means that every time you fix an element W in little g, you can actually think of this object here as a vector field on the whole group. And the value of the vector field at the point G is the associated tangent vector at G being G times W. So this is an important point. So every time you fix an element of the tangent space of the identity is fixed in just one tangent vector in one tangent space, you can identify it with a smooth vector field on all the group. And the value at some point G is just your tangent vector of the identity multiplied by G. Okay, so every time you choose an element in here, you actually have a smooth vector field on the group. So you can try to integrate. If you have a smooth vector field, you can try to find the flow whose generator is this vector field. So this is what we are trying to do now. And for this, I have to recall what the matrix exponential that you might have seen in some calculus class before. Anyway, it's defined as usual as the infinite series. And now we notice that one of the properties of this matrix exponential is that the determinant of the exponential of a matrix is equal to the exponential of the trace of the original matrix. So if I take an element in little g, its trace is 0. So the exponential of 0 is 1. So the determinant of the exponential of that matrix has determinant 1. So this means that anytime I take an element in the tangent space of the identity and I compute the exponential, I end up with an element in SL2R. So some examples again. So recall U was the matrix 0, 1, 0, 0. So let us now take T times U, where T is any real number. So I get the matrix 0, T, 0, 0. What is its exponential? I have to compute this series. But then I notice that as soon as I square this matrix, I get 0, and I keep getting 0 every time I take a higher power. So this infinite series here is actually a sum of just two terms, because from the second term on, they are all zeros. So it's just the identity plus this matrix. I get the matrix 1, T, 0, 1. If I do it for my old matrix X, that was 1/2, 0, 0, 1, minus 1/2. Now I just multiply it by T. I do the exponential. Well, the exponential of a diagonal matrix is a matrix whose diagonal entries are the exponential of what was in there. So the exponential of this matrix is the matrix is a diagonal matrix whose entries are the exponential of these guys here. So I get all this collection of elements in here. And maybe you could do the same with little b that was 0, 0, 1, 0, and you would get 1, 0, T1. But let me just give another example. This is maybe less immediate to see, but you can convince yourself that if you take R to be 0, minus 1/2, 1/2, 0, and then multiply by T, and you compute the exponential of this matrix, so you compute this infinite series, you end up with this rotation matrix. So cos of T over 2 minus sine of T over 2, sine of T over 2, cosine of T over 2. So I can define, for every element in my little g, I can define a flow that I will call phi of W for any time t in R, just by at the point G, I multiply on the right by the exponential of TW. And so this is a collection of math, but you can actually check that this is a flow, so it satisfies the group relation. So t equal to 0 is the identity, and phi of c plus s is phi t composed with phi s. Okay, so for example, phi of u would be, phi t of u would be the multiplication on the right by this matrix. Phi x of phi x at time t would be the multiplication on the right by this matrix here. And phi r of t would be the multiplication on the right by this matrix here. Okay, so at the point you multiply on the right by the exponential of t times the matrix you chose in your tangent space at the identity. And it turns out that this is actually the flow we were looking at. So this is the flow generated by the vector field capital W that was the vector field associated to this element that you chose in the Lie algebra. Indeed, what do I need to do to check this claim? Well, I can just take the derivative as 0 of the map VWT. I have to differentiate at 0 G times the exponential of TW. And if I differentiate these at t equal to 0, I get exactly W. So I get G times W. And this by definition was the value of my vector field capital W at G. Okay, so to repeat once more, we looked at what is the tangent space of the identity. Every element in here determines a vector field on the group. And the integral curves of this vector field are given by multiplication on the right by the exponential of t times that matrix you chose. And in the following, I will identify this vector field with a derivation. This is a classical language in differential topology. So this is a derivation. So every time I have a C1 function on G, the value WF at G is the derivative of F along the direction of the flow phi t W. Okay, this is a shorthand notation if you want. So I can think of elements in the tangent space of the identity in 3 ways. I can think of them as tangent vector as the identity. I can think of them as vector field generating this flow. I can think of them as derivations of functions. Is everything clear? Okay, so these are my flows. These are the homogeneous flow, the flows I want to study. But it turns out that this space is too large. So we want to go to some smaller space. So in particular, I want to go to quotients of the group G to make the space smaller. So what do? We take discrete subgroups of G. And it turns out that the quotient of G by a discrete subgroup, and I will take a quotient on the left. So elements, I will denote the quotient by M, and elements of these quotients are left cosets, so are objects of the form gamma times an element of my group. So this algebraic quotient turns out to be a smooth manifold. So it's a nice geometric object. And just a brief sketch of the proof, how does it go? Well, by assumption, if the group is discrete, then it acts properly discontinuously on G. So this means that for every compact neighborhood of a point, there are only finally many images of that point under the group of isometries. So every point has a small neighborhood under which there are no other elements of the orbit under gamma of that point. So this means that the canonical projection from G to the quotient is a covering map. So since you have a covering map, then you can define a smooth structure on G just by composing with the local inverse of your projection. Does that make sense? This is a brief sketch, but I hope it's clear. So locally, so this space M is a quotient, but locally it looks like G. locally it looks like a local neighborhood of G itself.
So, maybe it's just like when you take gamma and x to z.
Yes.
So what about these singular points like this I and
They are still, so geometrically maybe you have some conical singularity, but homomorphically they are the same. Yeah. You might have some finite order guy, but locally it's still an open ball. Geometrically is, yes, you have a singularity. This is just to define charts. So no, sorry. No, I should say this. This I'm talking about the quotient of G, not of the hyperbolic. So you're thinking of a quotient of G mod SO2. So the modular surface has a singularity, but G mod SL2, SL2R mod SL2Z, I think it doesn't. All right. So a remark is that since I'm taking left quotients of G and my flow phi W of T was defined by multiplication on the right, so this flow that was defined on G is actually also well defined on the quotient M. Because again, I have a left quotient and I multiply on the right, and left and right commute. So I had these homogeneous flows that were defined on the group, but I can actually define on any quotient by a discrete subgroup of G. And for the rest of the course, I would be interested only in quotients that are compact. There are quotients that are infinite volume. Well, I haven't said what the volume is yet, but there are non-compact quotients. I will restrict only to compact ones.
Give an example.
Can I give an example? Not an explicit one.
I mean, take something.
So I cannot write down any explicit, but so if you...
Well, it's a three-dimensional manifold. So, right?
So I will come later to the connection with hyperbolic geometry, but so if you take an ideal polygon in the hyperbolic plane, and you look at the group of the reflections of the sides, and you choose your polygon nicely, so like a regular octagon, for example, the group generated by this reflection would be...
No, but this is the portion of the plane, right?
So I'm saying the group of those... Yeah, I'm saying the group generated by this reflection,
yes,
will have the property that this quotient is compact.
Yes, but this is a three-dimensional manifold.
Yeah, but this three-dimensional manifold is just right.
Yes, I will. Yes, I will.
It's a unique tangible bundle of this two-dimensional thing.
Yeah.
If the base is the tangible bundle.
I will come with the geometric picture in a second. So far, it's just algebraic. Yeah. So the example that was mentioned before, SL2Z, is not an example that I would be interested in because it's not. Okay, so we have our space, we have our dynamics of this homogeneous flow. Now we want to measure. So I want to briefly tell you what our measure is and how it's constructed. So let me give an idea. So recall that for every point in G, we can identify the tangent space at G with the tangent space at the identity. And the identification was the multiplication by G. And for example, we found before a basis for my tangent space at the identity being those three matrices U, X, V. So I fix the basis of my tangent space at the identity, so I can identify it with R3 with respect to this basis. And then since all these guys are identified with this one, I can identify all these tangent spaces with R3. Okay, I made a choice here, but bear with me. all these tangent spaces are identified with R3. So I will define omega g by doing the following. So every time you take 3 vectors in the tangent space at G, W1, W2, W3, and say the coordinates are U1, X1, V1, U2, X2, V2, U3, X3, V3. I will define omega g of these 3 tangent vectors at G to be the determinant of the matrix whose column are the coordinates with respect to this basis. Okay, this is, I'm defining it in this way. So what is this object? Well, this object is it's something that takes 3 vectors in the tangent space at G and gives me back. So for any fixed G, omega takes 3 vectors in the tangent space at G and gives me back a real number. And since it's defined using the determinant, you can see that this function here is bilinear it's multilinear in the entries, and it's alternating. So in the language of differential topology, this omega is a differential 3 form on the group. Okay, and it's a smooth because it's smooth in the coordinates. So every time, G is a 3-dimensional manifold. I have a 3-dimensional, I have a 3 form. So I can define a measure just by declaring that if I take a continuous function with compact support, the value of the integral of the function with respect to the measure I want to define is given by integrating f times the absolute value of this differential form. And this is what I call the R measure on the group. And so this is how it's defined by hands. And
is it important that you started from a very particular triple, or?
No, exactly. So the proposition that I did not prove, but it says that this measure has properties. So let me start by addressing your question. So up to scalar multiples, it is the unique measure with this property. So where does this come from? Well, okay, at first I made the choice of the basis. But if I change the basis, the determinant changes only by a scalar. And so the choice of basis only matters in a scalar. And this is where the up to scalar comes from. And actually, one of the defining properties of the determinant is that is the unique multilinear alternating form. So
if you change the base, then the scalar is just the determinant of the
change of basis. Yes, exactly. So what it's interesting for us is that, okay, so it is the unique measure that satisfies the previous property, but also in this statement, I'm saying that the choices that we made at the beginning of the basis only matters up to a scalar multiple that in the end we will not care because we will go to compact quotient. So this measure will go on the quotient and we will take it to be a probability measure. So we will fix the normalization so that the total measure is 1. And it has 2 other very nice property. Well, one is what I was mentioning, the fact that it's also defined on quotients, because again, this is given by integrating a differential form, which is a local operation, and locally M is like G. So, so it's invariant also by left multiplication. So it's well defined on the quotient, and is also invariant by multiplication on the right. So one of the properties of this metric is that it is invariant by right multiplication, and all these flows were defined by multiplication on the right. So this is an invariant measure for all my flows. So it's a nice measure with respect to which we want to do ergodic theory. So it's a smooth measure. It's defined by integrating a smooth differential form, and is an invariant measure for all my flows that I want to look at. So now we are set. We have defined our flow. We have defined the spaces, so these quotients here, and we have our invariant measure with respect to which we want to study the ergodic properties. And in the starting from next lecture, I will, of all these possible choices of flows, where you can choose any element here in little g, I will choose W to be the little u that we defined before. So the matrix 0, 1, 0, 0. So the Horocycle flow will be the flow defined in this way by choosing W equal to U. So multiplication on the right by the matrix 1, P, 0, 1.
So,
Yes.
sorry, so this proposition is true because you assume the quotient to be compact, or
No, this is true in general.
so you don't need like a finite volume of the quotient to have invariance.
You need the existence of a quotient, a finite volume quotient. Yes.
Right, because you want it to be invariant on the left and on the right.
Yeah. So the group needs to admit a lattice.
Okay, okay.
So
And probably you should assume that you deal with random measure.
yes.
This is
Yeah.
the only additional point.
Oh, yes. When I said it is the unique measure, I mean yes. Okay, so maybe here I've been a bit sloppy in stating this, but for our purpose, it will be the unique measure. That's but so yes, hidden in the proof of this proposition, there is the fact that to be invariant by multiplication on the right, you need G to admit the lattice, which is a true fact, and then you can. So the group is unimodular. So if it is left invariant, it's also right invariant. And so the left invariance ensures that this is well defined on the quotients, and the right invariance ensures that it's invariant by all these
So
flows.
you have at least one lattice and everything.
Then the group is unimodular. And yeah, this is the measure we will be looking at. Thanks for the question. Okay, so this is what I want to. So I mean, this are all the definitions that we will need during the course. So as I mentioned, we will be studying the ergodic properties of this flow by choosing W equal to U on quotients of this form, which are compact with respect to this measure here. Okay, now in the second part, I want to define some more objects that will be useful later. Other questions so far? I want to define some more objects that will come useful later. So the adjoint action, the Lie brackets, the killing form, and the Casimir operator. Okay, so let's start from the adjoint. So it's a fact from linear algebra that if you have two matrices, the trace of W times Z is equal to the trace of Z times W. So this is a simple observation, but it tells us something. So for example, my group can act on G by conjugation. So for any G, I can define a map that I would call at G from little g to itself by taking a matrix W and mapping it to G inverse WG. You can check that this is a linear map. It's invertible. The inverse at G inverse associated to G inverse, and it maps little g into itself. Why little g are all the matrices with zero trace, and by this property here, the trace of G inverse WG is the same as trace of W. So if the trace was zero, the trace of this matrix is also zero. So for every element of my group, I have a linear automorphism of my little g by conjugation. And the second consequence of this fact is that G is also closed under another operation that I would call the bracket operation. That is, take two elements in G, W and Z, and the bracket of W and Z is W times Z minus Z times W. And again, if the trace of this matrix on the right hand side is zero, so this is again another element of my little g. So G is a vector space. And now I also have this operation that it's a bilinear operation. So from now on, I will call little g an algebra. I will call it the Lie algebra. And the algebra comes from this operation here, this bracket operation. Okay, so we have these two objects that come from this observation. Can we interpret dynamically what these things are telling us? Okay, so let us first try to find an interpretation for my add of G. So I haven't said it, or maybe I said it, but without stressing it. So I will call add G the adjoint of G. This is the name. So let us try to find an interpretation for the adjoint. So imagine now that the element G for which you are computing add of G is the exponential of a matrix T times W. Okay, so this is again a linear automorphism G that takes an element here and maps it to the inverse of this matrix, which is the exponential of minus T times W times the input you take times this matrix again. And this is an automorphism from G to itself. But I can also think of it, or I mean, this under the identification of the tangent space at G with the Lie algebra G, the adjoint actually coincides with the differential of the time T map of my flow. Okay, so the time T map of my flow, recall, was the multiplication on the right by the exponential of T times W. So the TW of T applied to some element is that element times the exponential of T times W. So its differential, say at the identity, so maybe here I should have write a differential at the identity, takes a tangent vector at the identity and maps it to a tangent vector at G. But then a tangent vector at G can be thought of as a tangent vector at the identity by multiplication on the left by the inverse of G, which is the exponential of minus TW. So if you take the differential of this map under the identification of this with little g by multiplication on the left by the exponential of minus TW, you get exactly the adjoint. Okay, so this algebraic operation, dynamically, it corresponds to the differential of the time T map of my flow. Does this make sense? So this computation that you can do by matrix multiplication is telling me if I apply the time T map of my flow, how it acts on tangent vectors, say at the identity. But then it will be the same for all other points.
I'm sorry to interrupt. I think I get the ideas, but it could be more helpful for you to maybe write it down.
Write down the proof of this, or
because you explained the matrix by words, it's kind of
so I'll try to sketch. Okay, so imagine that. So this object here then take a tangent vector at the identity and maps it to a tangent vector at G. So here you have the identity, and here you have G being the exponential of TW. Imagine now that you have a curve here, and here I have my tangent vector. So this is gamma T, and this is gamma prime of 0. So if I apply my phi W of T, so here I get a new curve that is gamma T times X of TW, which is phi W T of too many gamma, so maybe call it S, this one, of gamma S. So the tangent vector that I get here, I have to differentiate this expression with respect to S. So I get gamma prime of 0 times x of tw. This is this tangent vector here. This is the tangent vector here. And then I can identify this tangent plane with this tangent plane. So from here to here, I take any vector here, and the corresponding vector here is g times that vector. So to see what this tangent vector here is in this tangent plane, I have to take this and multiply it on the left by the inverse of g. So the associated tangent vector here is x of minus tw, gamma prime of 0, x tw, where this is g inverse. Does this make more sense? So multiplication on the right by g acts like this on tangent vector. So if you identify this back with itself, you get precisely the expression for the adjoint. Thank you for your questions. Okay, and so this is a dynamical interpretation of my adjoint. So what is the dynamical interpretation of my bracket operation? Okay, so if I take this adjoint, so remember, so this is the differential of the time t map. And now I can try to derive this with respect to t, at t equal to 0. Okay, so if I just expand this term in here, so this is x of minus tw times z times the exponential of tw. I have to differentiate at t equal to 0. Just by doing some algebra, I get minus w times z plus z times w, and this is exactly minus the bracket of w and z. So the bracket of w and z is precisely the derivative of the adjoint of the exponential of minus tw, which under this interpretation was the differential of the time t map at time minus t, differentiated t equal to 0. Does this make sense? So the bracket is the differential at 0 of the capital adjoint, or capital adjoint at x of minus tw, that under this identification is the differential at 0 of this guy here, phi w at minus t. And if you've seen some differential topology before, this is the definition of the Lie derivative. So the Lie bracket of w, and now I think of this as a linear map, and I will call it little ad of w. So this is the little adjoint of w. So this is the linear map that takes a vector and computes the bracket of w with that vector. This is, again, a matrix multiplication, but dynamically, it corresponds to taking the Lie derivative with respect to my flow, or my vector field defining my flow. And again, taking the Lie derivative is telling me, so here I'm taking a derivative with respect to time at t equal to 0, so it's telling me infinitesimally how my flow moves tangent vectors. Okay. Okay, let us see some example. For example, fix this basis of my Lie algebra G. So this is a basis of the space of 2 by 2 matrices with 0 trace. So this R, my friend X, and a new guy that I will call Y, 0, 1/2, 1/2, 0. So once I fix this basis, so now I change the basis with respect to the basis I chose before, I can identify again my space G with R3 because any element is a linear combination of these three guys. So I can try to look at, for example, the map that takes a vector and computes the bracket with R, or the linear map that takes any other element and compute the bracket with respect to X, or the same with respect to Y. So these are linear maps on R3. So they are represented by 3 by 3 matrices. So I can compute them because the bracket again was R times the matrix minus the matrix times R. And if I did it correctly, I get this matrix here. So this means that on the first column is the value of the bracket of R with itself, which is 0, because it would be R times R minus R times R, that is 0. The second column tells me that if I do the bracket of R with X, I get 1/2 Y. And the third column tells me that if I take the bracket of R with Y, I get minus ½ X. And I do the same for this too. So bracket of X with R minus ½ Y, bracket of X with X is 0, bracket of X with Y is minus ½ R, and so on for the third one. Is that clear? So this is a computation tool. But I need this computation to introduce another object that is the killing form. So the killing form is a bilinear form on the Lie algebra, my place G, and is defined as follows. So in the bilinear form, I take two elements in here, and I compute the following. So I compute the matrices associated to the adjoint of those guys. I take the product of these matrices, or if you think of them as linear map, you take the composition of these two linear maps, and then you take the trace of whatever you obtain there. And I put the two just because it makes what comes after nicer, but the two here is not important. So the killing form is defined, you take two elements in the algebra, you compute the associated 3 by 3 matrices that corresponds to doing the bracket with respect to the vector, take the product of these two matrices and look at the trace. So for example, if I want to find the killing form of R times X, I would have to take the adjoint of R, multiply it on the left by this matrix, take the trace and multiply by 2, and so on for all the others. So with respect to the basis I chose before, I computed the matrix before, so I can do it. I take all the possible products, compute the trace, multiply by 2. And I get that this bilinear form is represented by this matrix in here. This is why instead of the basis I chose before, I chose this different basis R, X, Y.
R is diagonal or?
R was the rotation. So this guy here. This is R, this is X, and this is Y. I obtained this very nice diagonal matrix here. And in particular, this is telling me, since it's diagonal and all the entries are non-zero, that this bilinear form is not degenerate. So why am I doing this? Well, because with the use of this bilinear form, I can come back maybe to some points that were raised before. I can find a nice geometric interpretation to all of these objects. No, first I need one more fact. So recall that G was acting on the Lie algebra by conjugation. And it turns out that the killing form, so this form is invariant by this action of G. So if you take two elements in your Lie algebra, W and Z, and you compute the killing form, B of W and Z, this is the same as if you were computing the killing form of G inverse WG and of G inverse ZG. Okay, so this is I put a sketch on the proof, but it's computation. I will put the slides online so you can check, but it's some computation that tells you that this bilinear form is invariant by conjugation by elements of G. So why do we like this? Well, this tells us the following. So I consider the set of R3 of all vectors, Z1, Z2, and Z3, such that the bilinear form I defined before is equal to -1, and the first one is positive. So if you want explicitly, these are all the points in R3, such that Z1, Z2, Z3 in R3, such that Z1 squared minus Z2 squared minus Z3 squared is equal to 1, and Z1 is positive. So this set over here, if you keep it with this distance over here, so the distance of the point being the Haar hyperbolic cosine of this quantity here, it's a model of the hyperbolic plane. It's the hyperboloid model of the hyperbolic plane. So I made a schematic picture. So this would be this set in what used to be light blue, now is, I don't really know what color, is this set H. This is the set of points in R3 such that this condition here is verified. And this is the so-called the hyperboloid model of the hyperbolic plane. There are some other models for the hyperbolic plane that you might have seen before. One other model is the so-called Klein models, that is the interior of a disk. Another model where, again, the space is the interior of the unit disk is the Poincaré model. And here in red, I drawn some geodesics in all these models. So in the hyperboloid model, a geodesic is the intersection of the hyperboloid with the plane going through the origin. With the Klein model, a geodesic is again the intersection of the plane with this disk. And with to get the corresponding image in the Poincaré model, you have to take, if this is the origin, you have to take a point down here, -1, and do a projection in this way. And you get semicircle in this way. Anyway, so what we care about is that we have this set that is with this distance, which is the model for the hyperbolic plane. And we have that G was acting on that set by conjugation. And we can actually prove the following. We can prove that G acts on that set by isometries. And not only G, but also the quotient of G by plus or minus the identity. So PSL2R acts on the hyperbolic plane by isometries. We can see that the action is transitive and it's not faithful. The stabilizer of one point, for the point 1, 0, 0, is the rotation subgroup, is SO2. Maybe let me briefly say why this is true. So G is connected. So G was acting, so recall, G acts by conjugation and preserves this bilinear form. And this model here was defined as vectors in R3 such that the bilinear form was equal to -1. So if I act by conjugation, I'm not changing the Killing form. So I'm still an element in here. And the distance is defined by the arc quotient of this bilinear form. So the action of G preserves this distance. So it acts on H by isometry. The fact that this is positive follows from the fact that G is connected. So G acts on the hyperbolic plane by isometries, and the adjoint of minus the identity is the identity, because multiplying on the left and on the right by minus the identity is doing nothing. So the action goes to this quotient. And again, since the adjoint preserves the Killing form, it is an isometry with respect to the associated hyperbolic metric. And to prove that it's transitive, you can verify it by hand. And recall that this was the generator of this. So the exponential of T times R was this subgroup. And it turns out that multiplying by the exponential of this guy on the left and on the right commute with this guy itself. So the stabilizer is SO2. I'm going a bit faster on this part, but yeah. So what this proposition is telling us is that we have a transitive action of G over PSL2R on H, with stabilizer at the point is the group SO2, the group of rotations. So this is telling us that G modulo SO2 can be identified with the hyperbolic plane. And I will not give you the proof, but it turns out that you can actually do a bit more. You can actually prove that PSL2R can be identified with the unit tangent bundle of the hyperbolic plane. And the information contained in the rotation subgroup gives you the orientation of the tangent vector. The quotient of G by a discrete subgroup can be identified with the unitangent bundle of the quotient of H by the same subgroup. So this is maybe an address to the previous comment. And this is to give a geometric interpretation of some of these flows that we encountered before. So the flow associated to XX being the element 1/2, 0, 0, minus 1/2 corresponds to the geodesic flow. So it corresponds to moving along these geodesics. And the protagonist of the rest of the course would be this flow here generated by the element U that was 0, 1, 0, 0, corresponds to the stable Horocycle flow, which geometrically corresponds to the, I didn't draw a Horocycle here, but this Horocycle would be the intersection of a plane whose normal vector is parallel to to this cone with this guy here, and coincides with all the vectors whose geodesical infinity converge to the same point. But maybe I'll say more about this next time, and maybe I'll stop here and I will introduce the Casimir operator next time.
Questions, comments? Go ahead.
Why the name killing form? What does this form does intuitively to your forms in your transit?
Sorry?
The reason for the name killing form.
I think it was the name of person.
Sure, but that is there is a reason, I guess. Intuitively, what does it do to your points in the transit? Is something?
I'm not sure I have any intuition of why.
So intuitively, you cannot say anything about what is this form doing? To your
Yeah.
Sometimes, for example, killing form are positively defined. So in your situation, the signature is minus 2
It's not.
1. So if it is positively defined, that it plays a role of Riemannian structure or something like that.
It is, yeah, I will say something about this later in the sense that it's related to the hyperbolic Laplacian, and I will say it next time. The fact that
An answer, hyperbolic Laplacian.
Yeah. So also the fact that this form is non-degenerate. This is true in the case of SL2R, but in a general group, you can do the same construction. And it turns out that groups for which this form is non-degenerate are precisely the so-called semi-simple groups. So it's one characterization of semi-simple groups, the fact that this form is non-degenerate. But I cannot say I have an intuition. Sorry.
Done? I have more questions. So the translate. So it's for